Okay. So before I begin, I just wanted to clarify some notational inconsistency that I had in the last lecture. See, all this while we have been saying that the pole location is some minus conductance by capacitance. The minus sign was to signify the fact that the pole was in the left half of S plane, right? But if I write the pole like this, the transfer function I will have to write it as 1 minus S by P1, isn't it? Only then the pole location is at P1 and P1 itself is some negative, okay? But if I write the transfer function in this form, okay, then the pole location I'll have to write as plus D by C. Okay? I think in a couple of places I might have made some sign mistakes, so please take care. Cool. So yeah, so then in the last class we were looking at the issue of instability in negative feedback, and the motivation was the following. We saw all our single stage OTAs can be modeled approximately as a first order system because it has one dominant pole. But what was the problem with single stage OTA? It cannot drive resistive loads, so that's why we decided to cascade multiple such stages. But then we saw each stage will have its own dominant pole, so overall you have a higher order system, so it can be unstable. So that led us to this path to understand stability, and this is the classic negative feedback model we were looking at. And of course we know the closed loop transfer function is 1 by beta times the loop gain by 1 plus loop gain, right? And the loop gain itself is beta times P of S, right? And we saw if this was a first order system, then the loop gain magnitude plot looks like this. It's constant, starts from A0 beta and then falls off with a slope of minus 20 dB per decade, and this frequency we called as omega u, standing for the unity gain or the unity loop gain frequency, and quite often it is also referred to as the unity gain bandwidth. Or the UGB, okay? And for the first order system, what was this equal to? We calculated last class. What was the unity gain frequency? So beta A0 times P1, right? Great. And we also saw this omega u was also equal to the closed loop 3 dB bandwidth. Okay, and please remember this relation is valid if you have a first order system, okay? And if you have a higher order system, the closer the approximation it is, the closer it is approximate as a first order system, this relation is also equally valid. Great. And we also remarked that the unity gain frequency was DC gain times the feedback factor times the dominant pole, right? So this is where we stopped. So now we know omega u is beta times DC gain times dominant pole. So let us say I take the 5 transistor OTA. So you guys know what is the DC gain, what is the dominant pole. Can you calculate and tell me what is omega u? You guys know the DC gain for the 5 transistor OTA. You also know the dominant pole. So please calculate and tell me what is it. What is it? Beta times? Yeah. Why is it? I mean, what is the DC gain for the OTA? It is GM of the NMOS by some output conductance, which is basically the output resistance is R0 of the NMOS parallel to the R0 of the PMOS. And the dominant pole was the same output conductance by the output capacitance you have. So this was basically beta times GM of the NMOS by CL, right? So now let us say I take a cascode OTA. So what is this equal to? Huh? Why? Correct. Right. So like he's saying, I mean, the moment we go to cascode, what do we change in? I mean, what changes in the cascode structure? Only the R out changes, right? And here you see the effect of R out is kind of getting cancelled. So here also this is the same thing. Okay. So basically, if you sketch the magnitude of the loop gain, so for the 5 transistor OTA, say you have a moderate DC gain, and then it encounters the first pole and then drops off like this. This is my omega u. The moment I go for a cascode, I see that the omega u is still the same, but the cascode is going to have a higher DC gain. So how will the loop gain plot look like? Loop gain. This is loop gain, right? Omega is still the same, and it has to go at 20 dB per decade, so it will follow the same line, isn't it? And then you will have something like this. So this was basically for the 5 transistor OTA. This is for the cascode. Both of them have the same omega u. Dominant pole is different, right? Because output resistance changes. So DC gain changes, the dominant pole changes. Omega u still remains the same. I mean, logically, this is the same omega u. It has to go through this point. Slope is minus 20 dB per decade. So this has to follow the same line. I mean, this is not looking like a continuous line, but this has to basically do this only. And then wherever it intersects or it reaches the dominant pole. Is that okay? So basically you have a GM like this. So it will have its own output conductance, and say you have a capacitance at the output. So what is the best case value for G out? What is the ideal value for G out you want? R out is infinite. What is G out? Zero. Okay. So if that happens, what will happen to the dominant pole? So basically you will have something like this. Okay, this is the ideal plot you want, right? So basically ideally you don't want this guy. So if I apply some input Vi of S, what is V out of S? GM into? GM Vi is the current. This current has to flow only to the capacitor, right? So the transfer function is basically some GM by SCL. And I mean, let's say beta is 1 for now. GM by CL is basically the omega u, right? I can also write it as basically omega u by S. I told G out, I mean, ideally you want G out to be 0, right? You want infinite output resistance. So I'm saying what? I'm looking at an idealistic scenario where G out is 0.
But the whole grade will pass through that.
Which one?
Short G out, whole grade will pass through.
No, okay. G out 0 means there is no conductance, which means infinite output resistance. If R out is 0, all current will flow. Okay, it's inverse. So I seem to have something like 1 by S as the transfer function. So what kind of a block is this? It's an integrator. Okay. So bottom line is ideally a GM should behave like an integrator. Okay, it should not have any output resistance. It should be able to drive the capacitance. So, cool. Great. So again, let me write the closed loop expression. We have something like this. So when can I say if the system is stable? All the poles of this guy must be in the left half of S plane. Right? And again, loop gain is beta times A of S. So for a first order system, I'll write this again. For a first order system, where is the closed loop pole? You already saw that, right? Closed loop pole is same as the omega u. Same as no, I mean, okay, oops, one second. In terms of, I mean, don't go to GM, these are the only things we know, right? So what is that? We already saw that. Minus beta A naught P1, right? And this is obviously in the left half of S plane, so we saw already this is stable, right? So of course, if I have a simple first order system, I can do this and find out approximate as so if you have a simple system like this, you can find out what the closed loop pole and find it, but of course in practice you will have a higher order system. So obviously it's not practical to find the pole locations of this guy and make comments on stability. So it might be better if you can look at just the loop gain and make any conclusions about the stability of the closed loop system. So do you guys know some techniques which can help you say that? Yeah, I hear one Nyquist plot. What was it? Root locus? It's okay. RS criteria is it's too mathematical. Okay, and of course, see, the simplest thing is Bode plot. Okay, and I mean, personally, this is the order in which I feel the complexity increases, right? Basically, these two guys will give you complete information about the closed loop poles, right? But this is more simpler to plot, right? So we'll try to understand stability using one of these, and then try to see how we can use only Bode plot to understand stability, right? And usually, although it's done using Nyquist plot, I will take a different approach and try to do that using root locus, because for Nyquist plot you need to know complex analysis, Cauchy's integral, Riemann zeta function, all sorts of things. But as I will show, root locus is more intuitive. So again, I'm sure you might have seen this in some place. Okay, so if you're not comfortable drawing root locus, it's okay. That's not the point of the course. I'll just go through something to get some conclusions about stability. That's all. Okay. And I'll upload the lecture today. So if you're not able to follow the notes, it's okay. Just pay attention to what I'm doing. So again, the idea of root locus is it says where the locations of the closed loop poles are. That's all, right? And the closed loop poles are basically the roots of this equation, right? So basically, this is what we are supposed to solve. And loop gain, I will write it as beta times a of s, and a of s in turn I will rewrite it as a naught times some numerator polynomial by denominator polynomial. Okay, n of s is, I can write it as 1 plus s by z1 containing all the zeros. The denominator is a polynomial containing all the poles. So if I simplify it, I get d of s plus beta a naught of 0. So the root locus will tell where the roots of this equation lie. As you change, say this guy a naught. That's all, right? So it's basically closed loop poles versus a naught. So if I put a naught equal to 0, what happens to the equation? So the poles, basically the closed loop poles will be roots of this equation. And what are the roots of this equation? In terms of some poles and zeros? Huh? No, closed loop poles seem to be when a naught equal to 0, we find that the closed loop poles are the roots of this equation. Roots of this equation in terms of pole 0, what are they? Open loop poles, right? So this will be at open loop poles. And as you tend a naught to infinity, you will have n of s equal to 0. So this will be at open loop zeros. Okay. So I'll just use this simple rule and qualitatively sketch the root locus. Okay. So the point is this: as you change the DC gain from 0 to infinity, the closed loop poles will start from open loop poles and reach open loop zeros. That's all. I'll only use this information, and one more rule I'll explain later to plot the entire root locus. So let's start with simple case. A of s is the first order case. Okay. Oops. So this is the sigma j omega. This is P1. So as you know, the closed loop poles start from open loop pole, which is this guy, and has to go to open loop 0. So where is the 0 here? Infinity. Okay, minus infinity to be exact, right? So it will start here and just go there. That's all, right? And again, it's clear that for any value of the DC gain you choose, the closed loop poles are lying in the left half of S plane, and first order system is hence stable, right? This is the 100th time we are looking at this. Cool. So now let's increase the complexity. So let's say I have two poles now. Two poles. So again, as I change a naught from 0 to infinity, the closed loop poles will start from this and go to minus infinity. So here I'll just say one more rule. It turns out if the root locus has to lie on real axis, what is the condition? Do you guys know? It turns out if it has to lie on real axis, to the right of it, it should have odd number of poles and zeros. Again, it's not difficult to explain why that is so, but I will not do it for the interest of time. So I'll just say odd number of poles and zeros to its right. Okay, that's it. So now what that means?
So there is another formula, like what is the angle it is making?
It's okay. See, I'm not looking at the exact stuff, right? This is first rule seems simple, that it starts from open loop poles, open loop zeros. Second rule also, actually I don't want to extend, it's also quite straightforward. I'll only use these two rules and plain logic to construct the root locus plot. I'll not go into details. Okay. So what this rule says is, if the root locus has to lie, says here, it should have odd number of poles and zeros to its right. So how many poles I have here? 2. So obviously it cannot lie on this. Okay, is it not? Okay. So which means the only possibility is this, right? In this region I see only one pole to the right, so it's okay. So if this is the case, I know that they should start at these poles and go to infinity. Looks like they cannot go to infinity along the real axis. So where can they go to infinity? They have the entire S-plane, right? So it's like now we have this entire real estate. This land has to be divided equally among the two brothers. What do? You divide it equally, right? So what will happen is, you say, one guy will take the top half, the other will take the bottom half. So it basically does something like this. Okay. So now can you say if system with 2 poles, can it become unstable? I mean, I have only 2 poles here, right? This is the case, right? I am increasing the DC gain from 0 to infinity. Is the closed loop pole entering the right half of S-plane? No. Which means second order system, in negative feedback for any DC gain, it's going to be stable. Okay, but the problem is because, let me make some space here. See, if you choose a large DC gain, you see that the closed loop poles might lie somewhere here. So these basically are at some minus sigma naught plus j omega naught and minus sigma naught minus j omega naught, right? So if we apply a step input, something like this, ideally you want the system to respond it nicely like this. But now we have these complex conjugate poles. So what do you think will happen? If complex conjugate, obviously there should be some sinusoidal thing, so it might do something like this. Okay. I mean, without going to a lot of details, this should make sense, right? I have some complex conjugate poles, complex exponentials, some oscillatory behavior must be there, right? So it will do a lot of ringing like this, and obviously this is not good. So that is why we don't want the closed loop poles to lie on these complex plane. Where do you want the poles to be? On the real axis. If you have it on the real axis, this imaginary portion and sinusoidal portion is not there. So I'll just say good to have poles on real axis. So now let me take one more case where I have 2 poles and 1 0. So 2 poles, 1 0. So again, the closed loop poles will start from open loop poles and go to open loop zeros. So I have one finite 0 and one more 0 at minus infinity, right? So again, let's first look at the location of the root locus on real axis. Can I have the root locus here? I have total of 3 poles and zeros, fine. So here I cannot have. So then I'll have here. So it looks like one of the poles will end up at the 0. The other guy will go to minus infinity like this. Okay. And again, when we didn't have the 0, what happened? They were doing something like this. So now I see that they cannot go to this complex plane. One of them has to end up here, other has to go to minus infinity. So logically, what do you think should happen? I mean, it cannot go on like this. That much is fine. So basically it makes sense that it might do something like this, right? So one of them will end up here, other will go to infinity. that okay? I mean, what point this comes here, what angle it goes, that is immaterial. Just by plain logic, looks like this is the qualitative sketch, right? So now you see the moment you added the 0, if I have a large DC gain, where are the poles located? Huh? They seem to be lying on the real axis. Okay. Cool. So now let's become adventurous. Let's say I have 3 poles. So I have only 3 poles. So the closed loop poles will start at these locations and has to go to infinity. So first let's look at the real axis portion. So can I have the root locus here? I can have. I can't have here. And the other location is here. Okay. Now all of them have to go to minus infinity. So again, now I have the entire real estate. Now I have 3 brothers. I have to divide it equally. I'll say 1/3 for each of them, right? That's all. So I'll say you take this, you take this, you take this. I mean, logically, this each quarter, not each quarter, whatever. Each section is for each guy like that. Okay. So now you can see that if you choose a large enough DC gain, the poles are entering the right half of S plane, and this guy can become unstable. Cool. So now let me take one last case. So I'll have say 3 poles and 2 zeros. So 3 poles and 2 zeros. Okay. So again, first let's look at the real axis portion. So can I have root locus here?
Yes.
Fine. So it means here the alternate segments I'll have. So again, when I didn't have the zeros, they were doing something like this, right? Now I have 2 zeros, so which means they cannot go to minus infinity. 2 of them have to end up here, and this guy is already reached here, right? So they have 2 zeros and 1 zero at minus infinity. So this pole will reach the 0. So basically, which means these 2 guys will start to branch out like this, but finally one has to go here, other has to go to minus infinity. Is that fine? So again, in plain logic, it will do this. That's all. Okay. So now you see, if you choose a large enough gain, again in the presence of zeros, the poles can actually lie on the real axis, and this indeed becomes stable. Okay. So the lame analogy I give is, this is like having naughty kids at home without the supervision of parents. So they go all the way like this and become unstable. But the moment you have 2 adults here, they'll start become unstable, but finally they'll pull it. So basically the zeros are acting like some kind of magnets, attracting the poles and making them fall on them, and that's why this system actually becomes stable finally. Okay. So I'll use this guy. So let me use this plot and understand how we can comment on the stability using Bode plot. So again, this has 3 poles and 2 zeros. So let me roughly sketch the Bode plot. This is omega, this is magnitude of loop gain. So let's say it starts from start at some value. It encounters the first pole, so it rolls off at minus 20 dB per decade. It encounters second pole, so does something like this. Third pole, 60 dB per decade. So let's say after some point it encounters the first 0, so then the slope increases, and then say one more 0, yeah, minus 20 dB. So let me okay. Let me extend this down. Let me also sketch the phase plot. Okay, this is frequency, and here I am sketching the angle of the loop gain. So if I just had one pole, how will the phase plot look like? It will start from 0,
0 to
minus one pole. What is the phase it can give at infinity? Minus 90 or minus 180? See, let's say I just have something like this, right? S by P. So I'll put, basically to plot Bode plot, I'll do something like this. As omega tends to infinity, what can you approximate this as? I mean, not exactly infinity, at very large frequencies, how can I approximate this as?
minus j p1 by omega.
Yeah, it's basically P1 by j omega. So what is the angle contributed? Minus 90. Okay, so it will start from 0, go to minus 90. So if I have one pole, this is the case. If I have three poles, what will happen? Each pole will add minus 90 degree. So the phase can go to minus 270. Okay, but if I have a 0, this is plus 90 degree. So I have two zeros here. They will contribute plus 180. So basically I had three poles. They will try to make the phase go to minus 270. But I also have two zeros after the three poles. That will add plus 180 degree phase. So eventually it will go to minus 90. So I'll again roughly sketch the phase. So this is, let's say, 0, minus 90, minus 180, and minus 270. Right, so the phase, the phase basically tries to go to minus 270, but the moment it encounters the 0, the phase will increase, and then it will eventually reach minus 90. Just a rough sketch. Okay, cool. So let me erase this, or I'll keep it here maybe, or here somewhere. So let's actually focus on this point. So this basically corresponds to a DC gain of some A0 prime. Okay, at this point the closed loop poles are lying on the imaginary axis, right? So remember, the closed loop poles are the roots of this equation, and for a particular value of A0, which I am calling A0 prime, we have complex conjugate poles. So even if I put S equal to j omega, I'll be able to make it go to 0, because I know for some complex numbers this is happening. Okay, yeah. Notice again crashing. Just a second. Okay, let's see. Okay, yeah. So as I was saying, let's focus on these points where I see that loop gain evaluated at a complex frequency is minus 1. So what can you say about the magnitude? 1. And what about the phase? minus 180. So here, let's say this is the minus 180 degree line. Let me. So if I change the DC gain A0, so how do you think the magnitude and the phase plot will change? I mean, this is basically a loop gain evaluated at some DC gain A0. So let us say I keep changing A0. How will the two plots change, magnitude and phase? Magnitude will change, phase will not change. Is that okay? So now let us say I am looking at this particular value of magnitude A0 prime. So at that magnitude, I see when the phase is minus 180, the gain has to be 1. Okay, so basically I'll have to scale down the magnitude plot so that the gain is indeed 1. So let me scale this plot down and draw. So let's say something like this. Okay, so this is some A0 prime. Okay,
Not this one, right?
which one?
You wrote A0 prime over there.
Yeah, that's a DC gain, right? This is A0 beta. If you are.
I was just confirmed that both A0 prime are same or not.
Yeah. I mean, see, this is the root locus, isn't it? So one of the roots goes like this, other root goes like this. For the same value, I mean, this is the location of two poles. Okay. This is okay. So here I am making sure for some value of A0 prime, the phase is minus 180, gain is 1. So I see that I have another point here where A0 is say some A0 double prime, where this happens again. So the phase goes to minus 180 once again at this point. So at this point, let's say the gain is okay. Say, let me modify it so that oops, just a second. Okay, so at this point the gain should be unity. So let me scale that something like this. Okay. Something. Oops, or I'll have to draw it better. Okay, so this is the wheel. Let me. Actually, this is the gain. Okay, something like this. So this corresponds to some A0 double prime, where once again when the phase is minus 180, the gain is 1. Okay. So what is the speciality about this region? Can you look here and say? It's unstable, right? Basically, if I choose the DC gain in this range from the root locus, it's obvious that the system is unstable. Any gain less than that, it is stable. Okay, that much is clear from the root locus plot. So let's try to translate the same on the Bode plot. So remember, this is the region. Okay, if I change the gain in this range between A0 prime and A0 double prime, any magnitude plot which is lying in this region, that will correspond to an unstable closed loop system. Okay?
So in the first plot, irrespective of what the parameters, we'll always have it like till minus going to minus 270.
It won't exactly go to minus 270, right? Because
it will always be below minus 180. So will it always cross, like go to the right hand side of the plane?
I didn't understand the question.
Sir, is it compulsory for the plot to go to the right hand side of the plane?
Which plot are you talking about?
The
Bode.
first one, Bode, not Bode.
Root locus.
Root locus.
Yeah, it actually can go. I have chosen some position of zeros like that.
So it may or it may not.
It may or may not.
But sir, we'll always have minus 180 phase.
Yeah, that is okay. That doesn't say anything about instability, right?
So minus 180 doesn't phase implies that there will be some root.
No, that doesn't say anything about the root in right half of S plane.
Okay.
If the phase is 180 and the gain is 1, it just says we have roots on the imaginary axis. That's all. We don't know anything.
So having roots on the imaginary axis doesn't imply that it will go to the right hand side.
We'll see that, right? As of now, the only information about instability is if the poles are on the right half of S plane, it is unstable. That's all. Okay, so the point I'm making is any magnitude plot which is lying in this range, that will all correspond to an unstable closed loop system. Okay? And can you, let's say, I choose some magnitude plot in this region. When the magnitude becomes 1, can you comment on the phase? Huh? No, let's say I choose this plot. This is some magnitude plot, right? And for this plot, I know for a fact that the system is unstable, right? Because I have chosen the gain in this range, right? So for this plot, the phase is, magnitude of the phase is greater than 180. Is that okay? So the point is, for unstable, the magnitude of the phase of the loop gain at omega u, I'll just say modulus of it is greater than 180. Okay? So now let us say I look at this magnitude plot. When the gain is 1, the phase is actually much less than 180. So this is definitely a stable system. Okay? And what is this phase difference called? It's a phase margin. Okay? So now can you say anything about stability from Bode plot? What should I look for if I have to say about stability? I should just look at the phase margin, and if the phase margin is greater than 0, it is stable. Okay? So let me write that. So I'll basically, for stability, I'll find the loop gain where it becomes equal to 1, and that corresponds to some omega equal to omega u, and the phase at omega u, we'll say modulus of that must be less than 180. Okay? And phase margin is basically 180 minus this phase. This has to be greater than 0. Okay? So I'm sure you might have seen this before also, but as a point I'm making it, that's the reason I'm making this point again. So let us say I have a case where I find that the phase of the loop gain at some frequency is minus 180. Okay? And I find that the magnitude at that same frequency, no, it's say 10. So can you say the system is unstable or stable? So I'll give you three options. A stable, B unstable, C I have no clue. Why? Huh? So he's saying no clue. Anyone voting for unstable or stable?
Because it will lie on the GMI axis, and if the gain is more, it can go.
So what is the conclusion? Is it stable or unstable? Unstable. How many of you are saying unstable? Okay, 1%. So everyone is convinced it is stable? Okay, so let's see, right? See, what do we know? If the system has to be stable, the phase at the frequency where the gain is 1, that should not exceed 180. That's the only condition. Okay, so the information given to us is this. So looks like if I plot the phase response, so let's say this is the phase. At some frequency, the phase is 180. Right? And at that same frequency, I measure the magnitude, that is some 10. Okay? So now as I increase frequency, the magnitude will increase or decrease logically. For practical systems, it has to decrease. Okay? Something like this. So now I'll have to look at the phase at this frequency where the magnitude becomes equal to 1. So I know the phase at a frequency that is much slower. Can you comment on the phase at this frequency now? Huh? So basically now we have two possibilities, right? The phase can basically do something like this. If that is the case, it's definitely unstable. But obviously you can also have a case where the phase does something like this. In that case, it is actually having a good phase margin. And that's exactly the case we saw here, right? See here, this system, we are convinced that it has a good phase margin. But at the frequency where the phase is becoming 180, the gain is actually much greater than 1. Okay? So, what is the right answer for this now? Okay. So, this basically is unstable. Under what condition? The phase monotonically reduces. Okay, so and if the phase reduces monotonically, can you comment on the poles and zeros in the system?
Difference should be greater than 2.
Sorry?
Poles, number of poles minus number of zeros should be greater than 2.
No, nothing like that.
Correct.
What is it? No zeros. Okay. See, if the phase has to reduce, it only means that the system has only poles. It cannot have left half plane zeros. The moment you have a left half plane 0, the phase is going to shoot up. Okay. So this means that the system is an all pole system. If you have an all pole system without any zeros, if someone gives you this information, you can say for sure that it is unstable. But this can become stable the moment you introduce left half plane zeros. That is also important. Okay, so what happens if you have right half plane zeros? So,
In the all pole system, can we have zeros to the right of the
no, all pole system means there is only poles.
like instead of the all pole system, can we have a system where we have poles, then zeros in the origin?
Zeros at the origin,
So zeros like
right half plane.
Between the poles and the origin, we have the zero.
Okay,
What is the zero in between two poles?
that doesn't count, right? See, the phase has to reduce monotonically. Okay, sorry. The phase has to reduce monotonically. So that I can guarantee that if I don't have any left half plane zeros.
But for that frequency, there is some.
Yeah, but again, it depends on very specifics, right? It is possible. But one thing is for sure, if I don't have any zeros, left half plane zeros, the phase is definitely going to reduce monotonically, right? Of course, you can have some zeros much earlier where the phase increased and then the pole will make it fall. That is possible. That's some special case, but if you want to make a statement, right, and I want to put it in a textbook, I can only say that if the system only has poles, then the phase reduces continuously, monotonically, and in those cases, I can comment on stability here.
What is RSP?
So he is asking RSP zeros. Okay. So let us say I have left half plane 0. what will happen to the phase? It will start, okay. So can you tell me how the phase will look like?
At 90-degree phase.
It will go to plus 90, right? Now if I have,
Minus 90.
what will happen?
Minus.
It will go to minus 90. So everyone fine with that? And it is basically 1 plus j omega by z1, 1 minus j omega by z1. As omega tends to infinity, left half plane will contribute plus 90, the right half plane will contribute minus 90. Is that okay?
Yes, sir.
So the takeaway is this, right? So if you want to comment on stability from Bode plot, the only thing you need to look at is phase margin. Okay, if the phase margin is greater than 0, then you can say the system is stable. And also if you have an all pole system, you can make an additional comment that if when phase is 180, the loop gain magnitude is greater than 1, then also you can say it's unstable because the phase is going to reduce monotonically, and when the gain becomes equal to 1, the phase will in turn have gone below minus 180. Okay, but the moment you have zeros, we cannot say anything about this. Okay, so yeah, so we'll stop here and we'll continue later.